So I want you to picture a standard printed page, like in a book. Find the lowercase letter I and just kind of zero in on that tiny dot right at the top of the letter. Hold that image in your mind.
Right, just a tiny speck of ink.
Exactly. Now, if our massive sun, I mean, a star so ridiculously huge that you could fit a million Earths inside of it, if that sun were shrunk down to the exact size of that tiny ink dot, the Milky Way galaxy would still be the size of the entire Earth.
It's just, it's a scale that completely shatters our standard operating software, you know? Our brains really aren't wired to visualize numbers that large.
No, not at all.
So we have to rely on these extreme physical comparisons just to get a toehold on the reality we actually live in.
But the wild thing is, you listening to this, you aren't separate from this cosmic scale. I think we look up at the night sky and think space is, out there, separate from
It's
us.
like it's a ceiling.
Yeah. But the only place in the known universe with the extreme pressure and heat required to forge the heavy atoms that make up your body, like the iron in your blood, the carbon in your cells, is the nuclear furnace inside a star.
Oh, absolutely. The violent death of ancient stars is literally the only mechanism capable of fusing those elements together and scattering them across the galaxy.
So astrophysics isn't just a story about distant lights. It's the story of the end of your nose. Welcome to our deep dive into the very fabric of reality. Today, we are synthesizing some truly mind-bending insights to demystify the cosmos, break down some pretty heavy physics, and explore the future of humanity, all without making your brain hurt too much.
Hopefully. Because, I mean, we are quite literally stardust, built from the debris of dying stars. It's a profound realization. But to track down where we came from and where we are going, we don't even need to look into the deep universe yet.
Right, we can start right in our own backyard.
Exactly. Because you don't have to leave our solar system to find environments that completely defy our everyday understanding of physics and chemistry.
Oh, for sure. Take Venus, for example. It is a literal hellscape right next door. The surface temperature hits 1,000 degrees Fahrenheit, and the atmospheric pressure is equivalent to being a full mile underwater here on Earth.
It would just crush a submarine instantly.
Yeah, and the clouds are made of sulfuric acid. Yet somehow, in the 70s and 80s, the Soviet Union managed to successfully land their Venera probes there.
Which is still an incredible engineering feat.
Right. They actually transmitted photographs of that crushed, melting landscape before the landers were just completely destroyed by the environment. But why is it so extreme? From what I'm reading in the sources, it's not just because it's closer to the sun than we are.
No, not at all. It's the ultimate cautionary tale of a runaway greenhouse effect. Venus has this incredibly thick atmosphere made almost entirely of carbon dioxide.
Okay.
So visible light from the sun passes through that thick atmosphere and heats up the planetary surface. The surface then tries to radiate that heat back out into space as infrared radiation.
But the CO2 blocks it.
Exactly. Carbon dioxide is incredibly effective at absorbing infrared. So the heat just gets trapped. It builds, it bakes the planet, which releases more gas from the rocks, and that traps even more heat in this vicious, unbreakable cycle.
So it's essentially a planetary oven that locked its own door. That makes sense. But then you look further out at Saturn, and the fluid dynamics get completely bizarre.
Oh, the hexagon.
Yes. At Saturn's North Pole, there is a perfectly hexagonal storm, a geometric hexagon. It's a jet stream roughly 2 Earths wide. And NASA's Cassini mission captured photographs of sunlight glinting off cloud banks hundreds of miles high, right in the eye of this massive storm.
It's one of the most surreal images in the solar system.
And apparently, because the gas is so incredibly cold, the fluid dynamics behave entirely differently than on Earth. Like there's almost no friction.
Yeah, when you have gas circulating at hundreds of miles an hour without any land masses to disrupt it, and at temperatures hundreds of degrees below zero, the atmosphere behaves almost like a perfect fluid. The hexagonal shape emerges completely naturally from differences in the speed of the winds at different latitudes. It's a massive, naturally occurring geometric pattern born purely out of fluid mechanics.
And if we want to talk about weird mechanics, we have to talk about Saturn's largest moon, Titan. It has a thick atmosphere, the surface is nearly 300 degrees below zero, and it features actual open lakes, rivers, and seas.
But not filled with water.
Right, because it's so freezing they are filled with liquid natural gas, methane and ethane. And NASA is launching a massive octocopter drone called Dragonfly around 2028 to just fly around Titan. At first, I couldn't figure out why we would send a helicopter to a moon, But looking at the physics, flying on Titan is actually a breeze, right?
Oh, it is the easiest place to fly in the entire solar system. Titan's gravity is only about 14% of Earth, so roughly the same as our moon, but its atmosphere is about 4 times denser than ours.
So thick air, low gravity.
Exactly. If you strapped a pair of cardboard wings to your arms on Titan, you could literally take off just by flapping them. That's exactly why a drone like Dragonfly is the perfect vehicle to explore it.
Okay, but beyond the cool factor of flying a drone in space, we are ostensibly looking for life. Why spend billions to fly an octocopter over methane lakes when we're looking for life? What kind of life could possibly survive swimming in liquid natural gas?
Well, what's fascinating here is that it forces us to strip away our Earth-centric biases. We always assume life absolutely needs liquid water as a solvent to mix chemicals together.
Right, follow the water.
Exactly. But Titan is a planetary-scale laboratory for organic chemistry. It's packed with carbon-based compounds raining out of the atmosphere.
Raining organics, that is wild.
Yeah, so the question Dragonfly is asking is, could liquid methane act as the solvent for a completely different kind of chemistry? Could cell membranes form out of nitrogen compounds rather than the lipids we have on Earth? It really pushes the boundaries of what habitability actually means.
So we have all this wild chemistry happening on a moon we can actually visit. But how do we leap from understanding Titan to knowing the atmospheric makeup of exoplanets? I mean, planets orbiting entirely different stars trillions of miles away.
That's where the physics of light comes in.
Right, because there are over 5,000 known exoplanets, but mostly we just see them as pixel-sized shadows when they transit or pass in front of their host star.
Yeah, finding the shadow is step one. Step two is decoding the light that filters around the edges of that shadow. That's the science of spectroscopy.
Okay, let's unpack this, because reading the sources, the way my brain made sense of spectroscopy is by picturing a cosmic barcode at a grocery store. We aren't actually seeing the water or carbon, we're looking at the starlight itself and realizing that specific elements ring up a specific barcode on the light spectrum to read the ingredients of a planet trillions of miles away. Is that accurate?
That is a perfect analogy, and that barcode is rooted in quantum mechanics. When starlight passes through the atmosphere of an exoplanet, the photons of light hit the atoms in that atmosphere. Every chemical element, oxygen, carbon, water vapor, has electrons orbiting its nucleus. And those electrons will only absorb very specific wavelengths or colors of light to jump to a higher energy state.
So they eat certain colors.
Exactly. So if there is water vapor in the atmosphere, it absorbs the exact wavelength of light associated with water. By the time the rest of that starlight reaches our telescopes, there's a dark gap, a missing line in the rainbow, exactly where that specific color should be.
Because the water vapor essentially stole that specific photon before it could get to Earth.
Right. And the James Webb Space Telescope takes that starlight, breaks it into a spectrum using a prism-like instrument, and looks for those dark gaps. It's reading the missing light to sniff out potential organic molecules in the atmospheres of planets we will never physically visit.
What blows my mind is how long we've been doing this. In 1868, a French astronomer named Pierre Janssen pointed his instruments at our own sun and used this exact mechanism.
Oh, the helium discovery.
Yeah, he found a chemical signature, a specific dark line in the rainbow that didn't match any known element on Earth. They named it helium, after Helios, the Greek sun god, because it was discovered on the sun before we ever knew it existed on Earth.
This raises an important question about human ingenuity, you know. The fact that humans in the 1800s figured out the chemical composition of a star just by looking at the rainbow it cast. It is a stunning triumph of observation.
Truly.
And digging into the behavior of light doesn't just reveal the chemistry of the universe, it eventually revealed the structural mechanics of reality itself. Because light doesn't just carry information, its speed dictates the flow of time.
Right, which leads us directly to Albert Einstein. He realized that the speed of light, which is an absolute unbreakable constant, means that our everyday human understanding of time is fundamentally flawed.
Completely flawed.
We think of time as a universal ticking clock, completely unchangeable. But time bends, stretches, and warps based on speed and gravity.
Let's look at gravity first. Einstein proposed that space and time are woven together into a single fabric, space-time. Gravity isn't just an invisible magnetic pull. It is massive objects, physically warping and curving that fabric.
Like the classic bowling ball on a trampoline analogy.
Exactly. The mat dips down. That dip is gravity. So the closer you are to a massive object, the deeper into that dip you are. Light, and therefore time, physically has to travel a longer curved path through that distorted space.
Which means the closer you are to a massive object, the slower time moves for you. And this isn't just theoretical math. Right now, because your feet are physically closer to the Earth's gravity while your head is, your feet are in a slightly stronger gravity field.
Yep.
Your feet are literally experiencing time at a slower rate, making your head slightly older than your feet.
It is a fraction of a nanosecond, but it is entirely measurable, and then you have the speed effect.
Time dilation.
Right. The faster you move through space, the slower you move through time relative to a stationary observer. Astronauts living on the space station are orbiting the Earth at roughly 20,000 miles per hour. After a 6-month mission, they return to Earth about 1/100th of a second younger than they would have been if they had stayed on the ground.
And this relativistic weirdness is the only reason our GPS works, right? The GPS system relies on a network of satellites in high Earth orbit.
Yeah, and because they are far away from the Earth's mass, they experience less gravity, so their onboard atomic clocks naturally tick faster than ours on the ground.
But they are also zooming around the planet at 9,000 miles per hour, which slows their clocks down. NASA has to constantly adjust the satellites to calculate for both of those opposing variables simultaneously. If they didn't, our GPS would be off by about 6 miles in a single day.
You are relying on Einstein's theory of relativity just to find the nearest coffee shop.
But I do have to push back on one concept in the literature regarding reaching the speed of light. Wait, the sources say if a spaceship hits the speed of light, it would have infinite mass.
Yep.
I can wrap my head around time slowing down, but how can a spaceship suddenly weigh more than the entire universe just by going fast?
Yeah, that phrasing is a holdover from older physics textbooks, and you're totally right to push back on it because it creates a misleading mental image.
Like the ship suddenly turning into a galaxy-sized object.
Right, which doesn't happen. It's far more accurate to talk about infinite energy. As an object with mass accelerates, getting closer and closer to the speed of light, the resistance to further acceleration increases. It requires increasingly more energy to push it even a millimeter per second faster.
Oh, I see.
To push a physical object all the way to the absolute speed of light would require an infinite amount of energy, literally more energy than exists in the entire universe. That is the barrier.
So light speed is the absolute speed limit of causality. And this framework led Einstein to a deeply unsettling conclusion about the nature of existence. He believed that the past, the present, and the future aren't happening in a strict sequence. They all exist simultaneously in one block of reality.
The block universe model, yeah.
He called our perception of time passing a persistently annoying illusion.
Because if observers moving at different speeds disagree on the exact timing of events, then there is no universal now. Every moment in time is just as real and persistent as every point in space.
And if time is a flexible illusion, then space itself is just as fragile. Which takes us to the most extreme objects in the universe where the laws of physics completely break down.
Like quantum entanglement.
Yes. Spooky action at a distance. You can take two subatomic particles, like electrons, and entangle them. If one is spinning up, the other is spinning down. You can separate them by any distance, even across a galaxy, and if you flip one, the other flips instantly.
Not at the speed of light, instantly.
Right. Space and time literally do not matter to them. Einstein hated this.
He was deeply uncomfortable with it because it seems to violate that universal speed limit of causality we just talked about. But we have proven it in laboratories over and over again. To those entangled particles, the vast distance between them simply doesn't exist. They are behaving as a single, unified quantum system.
So what does this all mean? Like, extrapolating that idea, if all the matter in the universe was compacted together into an unimaginably small point right before the Big Bang, is it possible that everything, including you, the listener, is currently quantum entangled to the rest of the universe? Are we universally telepathic on a subatomic level?
I love that leap of logic. If we connect this to the bigger picture, this might be exactly how super advanced civilizations travel or communicate. Not with clunky metallic spaceships, but by manipulating the entanglement of space-time itself to instantly affect something on the other side of the galaxy.
And we know space can be folded and crushed because we see it happen with neutron stars. These are the dead stars crushed down to just 20 miles across, but possessing twice the mass of our sun.
The density is incomprehensible.
A single teaspoon of a neutron star would weigh as much as Mount Everest.
At that density, the gravity is so extreme that it physically crushes the empty space right out of the atoms. Electrons get smashed into protons, and deep in the core, the pressure is so violent that even the neutrons themselves might break down. We call their interiors a quark soup.
Quark soup.
Yeah, because the fundamental building blocks of matter, quarks, are likely swimming freely, unbound by atomic structure.
And the gravity is so intense it literally bends the visual reality of the star. NASA operates an instrument on the space station called NICER to study them.
Right, the neutron star interior composition explorer.
It detects X-rays emitted by hotspots on the surface. But because the gravity is warping space-time so severely, it bends the path of the light. NICER can track a hotspot as it rotates completely onto the back of the star. The gravity pulls the light from the far side up and over the horizon, allowing us to see the back of the star from the front.
It's extreme gravitational lensing. The mass is physically distorting the path that the photons must travel.
And if you add even more mass to that scenario, space-time breaks completely and you get a black hole. We have a supermassive black hole at the center of our Milky Way galaxy. It's 4 million times the mass of the sun.
Sagittarius A star.
We can't see it directly because not even light can escape, but we know it's there because we watch stars, like one called S2, whipping around an invisible dark point at 50 million miles per hour.
And recently, the Event Horizon Telescope took a picture of a black hole's shadow. But no single telescope on Earth is powerful enough to see something that far away. So they networked radio observatories across the entire globe, from the South Pole to Chile to the US, essentially using the Earth itself as one giant telescope lens.
But the synchronization required is mind-bending. Every single telescope had to record incoming light, time-stamped using atomic clocks precise to a fraction of a trillionth of a second. They had to compensate for the weather, the rotation of the Earth, just to catch the exact same photon of light simultaneously.
It's an incredible achievement.
They generated so much raw data, they couldn't even use the internet. They literally had to fly physical hard drives out of the South Pole on cargo planes.
We essentially looked into the abyss where space-time collapses.
Which brings us to the ultimate origin of that space-time. If we rewind from the extremes of crushed matter, we get to the ultimate compressed state, the Big Bang. And then we can fast forward to where humanity is heading next. But we need to clear up a misconception. The Big Bang wasn't an explosion in space. Space itself is expanding.
Right, think of pulling a piece of elastic with two dots drawn on it. The dots don't slide across the rubber. The physical material, the space between them, stretches. That's what our universe is doing.
And we actually captured the echo of this, the cosmic microwave background. Back in the 60s, scientists at Bell Labs built a sensitive microwave antenna but kept picking up this constant static.
This is one of my favorite stories. They thought the static in their telescope was caused by pigeon poop.
Right. They spent days scraping out pigeon droppings, convinced that was the noise. But it wasn't. What they stumbled upon was the uniform temperature of the early universe.
About 380,000 years after the initial expansion, the universe cooled enough for photons to travel. As space stretched, that light stretched into the microwave spectrum. Those tiny ripples in it are the fossilized echoes of ancient sound waves from the early universe.
A literal baby picture of reality. And while the universe expanded, the ingredients for life were falling inward. Look at NASA's OSIRIS-REx mission. They launched a probe to the asteroid Bennu. It autonomously dodged a field of boulders, vacuumed up dirt, and brought it back. And inside, they found the nucleobases of DNA and RNA.
It's amazing. The building blocks of life are quite literally raining down from space. The chemical components required for biology were forged in the cosmos and gathered on comets and asteroids.
So here's where it gets really interesting. If we are stardust that evolved into biological beings, where does this evolutionary trajectory take us next? The sources touch on AI, but they frame it in a way that shifts the paradigm. AI is not artificial. It is an earthling. It is our child, made from the elements of this exact planet.
It's a profound way to look at it.
It's like humanity is an electronic caterpillar.
Yeah.
We have this relentless biological urge to innovate and build, perhaps completely unaware that we are just spinning a technological cocoon to birth a superior non-biological life form.
It's a humbling philosophical pivot, for sure.
Yeah.
An advanced artificial intelligence might be humanity's evolutionary cocoon to transcend our biological tribal behaviors like war and resource hoarding. But as scientists, while we look at the stars, we must rely on what is reproducible in science.
Right.
But we also have to leave room for awe. The true mark of a scientist is the humility to say, we don't know.
Okay, let's bring this all back. We have covered a staggering amount of ground. We started as the dot of an eye compared to the galaxy, learned that our feet age differently than our heads, realized the building blocks of our DNA might have hitchhiked here on an asteroid, and looked ahead to a future where we merge with AI to transcend our primitive biology.
And while the math is incredibly complex, the sheer wonder is accessible to everyone. Science is about observing the measurables, which is why the experts keep a bottle of champagne chilling for the day they find reproducible proof of alien bacteria.
I love that. So to wrap up, I want to leave you with one final provocative thought to mull over. Let's go back to Einstein's block universe, the idea that the past, present, and future all exist simultaneously in a massive, unchanging block of space-time. If that's true, then this very moment you listening to this deep dive has always existed and will always exist. Your entire life is a permanent, unchangeable structure embedded in the fabric of the universe. So if your future is already written into the architecture of reality, what does that mean for your free will?